So from the last class let me see. So from last class we kind of like went through the algorithm for the logistic regression. So today we're gonna actually introduce the how we're gonna use that for the with MapReduce to implement it in the with big data. So just a brief recap. Okay, this is just want to make sure you guys still remember what we talked about in the last class. So for the logistic regression, we're starting by constructing the likelihood function, right? So we have this is basically right here. This is our likelihood function. Then in order to maximize it, we convert it to a so-called log likelihood, because the maximize the likelihood and the maximizing log likelihood, they are the same. Then to maximize this log likelihood, since it's a non-linear function, it's a non-linear system, we try to using the numerical methods to do that. So we introduce two methods. One is Newton-Raphson, which is depending on the first and second order derivative of the log likelihood. Second one is so-called the steepest descendant. So it's a gradient-based method. They are essentially the idea is the same, but they are different in terms of the convergence rate. So, but both we need to evaluate in the gradient for the log likelihood with respect to the parameter beta. So we have in it here and the first derivative and the second derivative, right? Then we have derived here. Now, the thing is, if we write them into the matrix form, the first derivative, right, the gradient can be written as x transpose y minus mu, which is mu is essentially is equal to n times pi. Pi in our cases ni. So we for each observation only have one. The ni equal to 1, so the mu actually equal to pi. So in this case, is your u vector, which is we also call it score vector, or the gradient, the first order derivative, they are the same, equal to x transpose y minus pi. So this is a metric form, right? We kind of went through to say the Newton-Raphson method, which is we also call the reweighted least square, can be written as a sequence of the iterative steps. At each step, the beta estimation or the beta update essentially is a weighted least square. So but this is a method has a caveat because in this method we have to calculate the Hessian matrix, which is involving x transpose dx. This calculation for this matrix actually is pretty computation intensive. So we introduce this gradient descendant methods, which is only require the first order derivative, right, or the gradient of the function f with respect to the parameter. In this method, we kind of avoid the computation of the Hessian matrix, but in this way, we also have another issue, which is we need to determine how to set up this is over gamma, which is we call it step size. When you try to for every step, when you try to update your parameter, how large you want to update it. Then we kind of go apply this gradient methods to the logistic regression. So this is basically the final formula. I think this is a slide we stopped with from last class. We have this is a formula, which is the first order derivative. We have in the u vector equal to x transpose y minus mu, which is also you can just view it as a pi. Now the update, okay, the update for the algorithm, basically we're starting with some random parameter beta 0. Then for each step, then we went through each step, right, iteratively. Now the first step is at t equal to 0, we update our pi first, okay. Once we update the pi, the mu is updated. Mu, if ni equal to 1, the mu is equal to pi, right? So then we don't, here actually don't need this is this dt, so this is the type we don't need that. because that's when I copied from the interruption, I accidentally forgot to forgot to remove it. So we don't need D, right? Because this is we already have this as a result. So then the update beta is so every time next step beta equal to the beta in the previous step plus gamma, which is our step size, some pre-specified, okay, the value. Or we can also talk about it like this is at this step we can also estimate. This is the gamma is a step size times the gradient. Then we keep updating as the argument with the argument before. If you update your beta in this way, your maximum your likelihood always goes up. So you continue this is iteratively from t. We continue until this is your likelihood function is does not increase like a log, right? It's just incremental is less than some specified the threshold epsilon, which is like 10 to the minus 4, 9 minus 6, depending on the accuracy you want to have. Now, then the next thing is we try to implement it right, in the algorithm. Before we do that, I want to set up I want to do a little bit setup for the algorithm. Now, okay, this is just for the people on the room. Okay, write a little on the whiteboard. So for the general, we have this gradient, right? We have the gradient. U is going to be equal to x transpose y minus. This is a so x transpose y minus. This is the pi t. Pi t is essentially equal to e to the power of you can see this is the x beta to the 1 plus e to the power x beta. Right. So this x is a matrix, right? Now you can say in this way we can actually simplify this. Well, not really simplify. We can just because essentially this is y can only pick two values, right? 0 and 1. Okay. So this is u vector with y is equal to 0, right? Or y equal to 0. So then this is essentially y equal to 0. This is y is gone. Then you only have negative sign then xt times this, right? So this is going to be equal to negative x transpose times e to the x beta over 1 plus e to the x beta. Okay. So this is which is if we divide this thing like q by the e to the power x beta, this actually can be equal to negative x transpose times 1 over 1 plus e to the negative x beta, right? And y is equal to 0. Okay. All right, so this is because in the second term, you divide the numerator and denominator by e to the x beta, then this is become 1. This becomes 1 over e to the x beta, which is e to the negative x beta, right? So this is pretty straightforward. Now, when y is equal to 1, okay, when y equal to 1, then what you have is this is going to be x transpose y 1 minus e to the x beta over 1 plus e to the x beta. Remember here, this are all vector operation, okay? But it can essentially the same as a scalar. Now, 1 minus e to the x beta essentially is equal to 1 over 1 plus e to the beta, right? So this second term is equal to x transpose times 1 over 1 plus e to the x beta. Right? Because you 1 minus is in the numerator, essentially because numerator become 1, the denominator stay the same. So it's equivalent to this. Now, if we change our y a little bit, okay, instead of using 0, 1 notation, because in most cases we denote as y as 0, 1, but there's no way saying we have to do this, okay? So if we change slightly, okay, let's say making this y equal to 1. Let's just say this is equivalent to, say, we introduce another parameter z, okay? When y is equal to 1, z equal to 1, but y equal to 0, z equal to -1. Now we change this is slightly. Okay. In here, this whole thing can be rewritten. Okay, this whole thing can be rewritten as z times x transpose times 1 over 1 plus e to the z times x transpose theta. Okay. You can see here you will introduce an extra variable z. Z is a scalar. Okay, z is a scalar. X beta is a vector. Okay, a scalar times a vector is still that operation is valid. Now, if we introduce a z, okay, if we introduce z in that way, then this is essentially this is equivalent to the above, right? Equivalent to the above, because when z is equal to 1, then this thing is when z is equal to 1, y is equal to 1, right? So it's gonna have x transpose 1 over e to the 1 plus e to the power of x beta. When z equal to -1, this is going to be equal to above, right? So it's the same. This is by doing this, just making our life a little bit easier. So we don't like when we do the coding, we don't need to do the like if else this statement. Okay, we can just do the one function. Now this gradient we can also write it. So if we define a function, okay, let's say we define a function g of a is equal to 1 over 1 plus e to the -a. Okay, what is that? This is just equal to e to the power of a to the power of 1 plus e to the a, right? Which is the logit transformation, right? Inverse of logit transformation. Because you have low, because in this way essentially is loaded a is going to be just logit of g of x, right? Logit of this is the g of a is equal to a, right? So this is the so g of a function is just essentially is a inverse logistic logit function. Now if we define this is a g of a is equal to this thing 1 over e 1 plus e to the -a. If we define the g of a equal to that, so this thing essentially this can be written as z times x transpose. It's going to be g of negative z times x beta. Right? Because the reason you have negative because I have a negative sign here. Okay, so then you can view this as a negative of negative, right? And this is then this is going to be g of negative z times beta. So this will be the basis we're going to use in for the coding, right? So it's a little bit I hope now you still follow it. So first we define a function g of a, which is 1 over 1 plus e to the -a. This function is the inverse of the logit function, okay? Because we're doing logistic regression, so that's what we try to define in this way. Now, when you're having this is for the first gradient, we first show this is gradient can be written as z times xt times 1 over 1 plus e to the z times x beta, right? We can write in this way for z equal to 1 equal to -1. Now, in order to make into this function, what we do is we can just do negative and a negative, right? We can do negative and negative, and become positive, and then this function essentially is g function of g on the negative z x function. Okay, so oh no, not x function, x beta, because x is right. So is Z times X transpose 1 plus, which is this thing is Z X transpose G of negative Z times X beta. So that's this is a function. Okay, this is a setup. Now, if you back to the slides, if we come back to the slides, okay, let's just first. So in order to fit in our algorithm into the for the big data, we're going to use in so-called iterative process with a Hadoop, right, with a MapReduce. So the first thing is we're going to have in the data in the disk. We go to the mapper. We then write to the disk. We then reduce the reader from disk and so on, right? So it's just iterative the MapReduce function. Now, how do we implement it? This is the algorithm. So first we define a function g. Okay, function g in here I'm just defining on the so function g is 1 over 1 plus e to the negative z. Okay, which is the function g right here. This is a function g we define, right? Define. So first we define this function g. Then in the mapper function, okay, in the mapper function, again there's ignore the in the mapper function, ignore the second key value. Okay, this is again, this is something I ignore this is scrambled. Okay, we don't need that. So in the mapper function, what we're going to do is we're going to update our gradient, right? We're going to update our gradient. So the mapper function is given like this. First, for each chunk of data, like we did it last time, right? The first column is going to be our index, right? So now the first column is our y. So we store our the data y in the first column. Then your x is going to be the rest of the matrix, which is data matrix, without the first column, right? Without first column, which is the rest of the column. So y is in this case y is ni by 1 vector. X is ni by p design matrix, right? This is our response. So the key value pairs in what we're going to do here, for each one of we're going to calculate our gradient. Okay, the gradient will be y times x. In here, the y in this definition, okay, in this definition, y is going to be defined as 1 and negative 1. Okay, so if a success, y we define as 1. If it's a failure, y we define as negative 1, which is equivalent to the z in the formula right here. Okay, so then you can see what we do here is z times x. Do x transpose. Yeah, I should be the this should be the this is y times transpose x. Okay, well, yes, so many typos. So it's going to be t, which is transpose. Okay, adding this guy, adding this thing here. So this should be y times x transpose g of negative y times x beta. Okay, so essentially what do you see this line right here is what we derive in on the blackboard. Okay, on the blackboard. So then this will be the gradient. Okay, you calculate the gradient, calculating for the segment for each segment data, right? Because for the MapReduce function, this is our data m, right? So then you have y, you have x, 1, 2. You divide your data into different segments. Each mapper function is going to process each segment, right? And your gradient can be added up, right? Your gradient can be added up for each segment. So that's why we have in this is a so the mapper function essentially is okay. We are going to calculate in the gradient. Now please make sure you make the correction, okay? Because later on we actually you don't need this. But this is just to make sure you have, and this is we don't need the second one because this is the key value. We just need this one key value. Then but this is x is x transpose. Okay, yes, this is the typo. Now in the second function, the reducer function, what we're going to do essentially, we just sum up. Okay, sum up. This is a gradient. Okay, so what the second do here? This is involving a little bit about the R operation, but what it does here basically essentially just sum. Okay, just sum up the the gradient. So in the okay, let me clear this up. So I'm gonna go back a little bit. So in here, what MapReduce doing, okay, is just to calculate the gradient. Okay, now we have the MapReduce, we have the gradient. Once we have the gradient, then the updating beta is easy. Okay, the beta updating is easy, so we don't need to do much work. The updating beta essentially is just this is a low dimension operation, right? Beta is a p by 1 vector, so this is updating beta. We don't need a MapReduce to update beta, but we do need a MapReduce. But we do need a MapReduce to do the gradient calculation. Did I do something? Now, in the for the logistic regression, for the gradient updating, okay, we can wrap it into a function called logistic regression. So in this logistic regression, we just need to have the input data, how many iterations we want to do, then what is the dimension of the data, and the gamma, which is the step size, right? We just need to specify this parameter. So in the logistic regression, first thing we will do, we initiate our beta to be some random the numbers. So then for I in 1 to iterations, for the iterations, go through iterations, then we calculate our gradient using the MapReduce, okay? Using MapReduce the formula to calculate our gradient. Then to update our beta will be equal to beta. I think okay. Here is here should be plus because there should be the plus. I will update the new version, right, with the correction. But this is because our gradient. I think what we do here is because I think I was thinking about like minimize the negative log likelihood, okay? But this is so the gradient is if it's related to the negative the log likelihood, then this should be minus. But this is a maximization problem, okay? So so the beta, each beta, what we're gonna do is gonna update it using beta gamma times the gradient. So this is our new beta. So once we have our new beta, then we can go back, right? We can go back to the previous MapReduce. Now remember here in the previous step, okay, this beta is the updated beta, right? Is updated beta. So every time when you update beta, so when the beta is coming to play in the next step is because when you update the gradient, your beta is a new beta. So this is the gradient. This is, you can see is actually it all converges to the algorithm is going to converge to the maximum. So when we return the beta, right? Return the beta. You can see the algorithm is actually not that bad, right? It's not that bad. The main algorithm, logistic regression, is just involving this is a for loop. This for loop is just two steps. One, you calculate the gradient, you update the gradient. Second, you update the beta, right? And the update gradient is a pretty heavy computation because when your data is large, you calculate this is the X trans beta is actually not that easy. Then this is a gradient calculation. We're using this MapReduce, right? We're using this MapReduce algorithm. Again, MapReduce is used to for the heavy lifting jobs, right? Which is in this case X beta is a heavy job. So we use that to calculate. Okay, so this is algorithm. In here, there are some details. Just ignore this is like from DFS. This have reduce equal to this is LR. The reduce combine equal T. These are the details for the if you try to implement MapReduce with R. Okay, these are the details with R. But then you from your point of view, because I know most of you just using the Python, we're gonna using the MPI for Pi. So this is the syntax. It does not really matter. Okay, so you just view this as like a pseudocode. So pseudocode, what it does is essentially we just update it. You have the input, you have the map function, you have the reduce function, and then you have some combine mechanism to calculate the gradient. And this is this procedure essentially is involving this is the mapper step is we calculate the gradient for each second data. Reduce is just sum them up. Okay, so that's all you need to like in here. There are also some details about like this is the R syntax. There are some details about how this works, but you from again from your point of view, you just know this is just a sum up. Okay, sum up all the gradients together. That's all. So all right, so you can see this is algorithm actually is pretty simple, right? Pretty simple. That's this is just even you implement this problem like a 20 lines code. That's you can do it for logistic regression. Okay. Of course, we didn't we kind of skip important topic here. Importance is the gamma. Okay. Like we talked last time, the gamma is actually a tricky part. Okay. If you really want to implement it, the gamma is tricky part because the gamma you don't want to be too big, you don't want to be too small, right? Because if it's too big, then if you update it, too big means every time you do the beta updating, you're gonna like updating them to be like the difference is gonna be large. If the difference is large, then you may overshoot. Okay, when your beta getting close to the optimum point. And if the beta is when the gamma is too small, then it may take a long time. Okay, maybe take a long time to updating. So the way to treat this gamma is we're gonna talk about it a little bit in the next chapter, which is about the optimization. Okay, so in the idea we do either we're gonna specify the gamma as decreasing. It's gonna decreasing with the iterations. Okay, it's become like at the beginning of the iteration gamma is large, and then it's becomes smaller and smaller to the end, or we can actually using another algorithm to find the gamma. Okay, to find the gamma. But this is the gamma is one. Let's just leave it for now. Okay, let's just assume we just using fixed gamma. We're gonna come back to talk about this gamma a little bit. This is actually not that straightforward. Okay, not that straightforward. But the core of the algorithm actually is, you can see, just one iteration, and this is one for loop. Inside for loop is a MapReduce plus the updating, right? So that's this is that. There you can try it. Okay, you can try it. You don't have to using the big data. You can try this algorithm just using the small data, just to get a sense, like write your own logistic regression. Okay, this is write your own logistic regression. I mean, it doesn't really involving a lot of heavy coding. It's probably half an hour or even less. Okay, if you really understand it, it probably took like even if the first time right, it probably like took a half an hour, 45 minutes for you to make it work. But I think is someone who is going to deal with the data analysis. I mean, it's a good practice. Okay, this is just for your own benefit. Because once you code it, you're gonna sort of like understanding all the why we do this, why we do that, all the like sort of small details. Okay, small details in the end. Then you can use it to compare within like the Python's logistic regression, right? So you can see what's how different it is. All right. Any questions regarding to the logistic regression algorithm and also its implementation? Good. All right. And any question from the on the Zoom? All right. Now, here's a question, right? Can we design a MapReduce program for logistic regression by using the Newton's method? Okay. The easy question, of course, is yes, right? Because then when we try to define the Newton's method, what's the difficult? Difficult is if we want to calculating the Hessian matrix is X transpose of XD is X transpose DX, right? So we need to calculate this matrix. This matrix is actually involving two calculations, right? X transpose D, and then with that times X. Because when X is large, then this is actually is a pretty computing intensive. That means we have to add in like two more MapReduce in our algorithm, right? Because that means when we updating this is a gradient, we have to also have another MapReduce to update our Hessian matrix, right? So then you can do if you use map, you can just do the Hessian matrix equal to value, then you're adding another MapReduce for the Hessian matrix computation. Then in here just minus the Hessian matrix times gradient. So that's it. So yes, you can do it. But then the question is, can you do it in a way that is computationally reasonably fast? Okay, computationally reasonably fast. So that's actually the challenge, right? That's actually the challenge. So the current method uses MapReduce to implement the logistic regression. So the limitations are either iterative process is pretty expensive and slow. Okay, and for every iteration is a MapReduce job. This is sort of like the nature of the algorithm we're currently using. And the input output, the MapReduce are both through disk, which is again is going to be slow. Plus, you have a time waiting in the queue, which making the pretty lengthy. All right. So then the question is, can we find a fitting method that can just simply scale with Hadoop? Okay. Or in other words, can we make use of the logistic regression methods, which is already being written in the package, okay, without writing our own code? Can we do that? Well, the question is yes, right? Because there's always a way to do that. Is so the naive way. What we can do is we can partition the data and then run the logistic regression on each partition, right? So you have a big data, right? You have a big data. 1 terabytes. Okay, we partition our data to like 1,000 1 gigabyte data. Okay, so you have 1,000 partitions. Each data contains 1 gigabyte of data. You have 1,000 of them. So then you can just run logistic regression on each segment of data. Okay, that's fine, right? Because now it's the 1 gigabyte data. You run logistic regression to it. That's no problem. So then we can just take the mean of learned coefficient. Right, so then you basically run like 1,000 logistic regression, and each regression, since it's on different sets of data, it can give you different coefficients, right? So then what do you do? I just take it. So I have 1,000 sets of coefficients. Okay, each of them will be slightly different, and I will just take the mean of the learned the coefficient, right? So you have in the parameter like is a 20 by 1, right? You have 20 by 1 vector for each segment data. So then you just take the mean of these vectors. But then what's the problem? The problem is there's no guarantee to converge, okay, to the model from single machine. Because now you basically what you do is you convert a problem into 1,000 optimization, small motivation, right? So on the small data. And then each data you're gonna optimize on that part of data, okay? But there's no guarantee the mean is gonna be the global optimization using all data, right? That's just simply not. We can then naive method again. Naive method is naive, but it has some value. Okay, if you don't have anything, if you don't have any resource available to you, if you have big data and you want to extract some information from data, the first method, this naive method, may be the best you can do. Okay, because see, you have a large data set. Let's not say the one terabyte, like say 100 gigabyte. Okay, so you can order even like a 20 gigabyte data, which is sitting on your laptop, and then you need to run a logistic regression on that data, which is if you 20 gigabyte data, if you run on your laptop, it won't work because it involving so much like intermediate steps. Even 25 gig data, your laptop is not going to be able to handle it. So you can just partition your data into like a small segment, again, just like what described in a small segment, and run logistic on each one of them, and just take the mean. That estimation, okay, is not an optimal estimation for sure, okay, but that estimation can still give you some information, okay, because you learn basically the difference is you have a big data, and you just learn it from like a small chunk of data. I mean, depending on how heterogeneity of the data, this small segment data may already recover like a lot of information from the big sample. Okay, the small sample may already has giving a lot of information about it. So even the naive method take the mean of the learned coefficient, it can still give you some good ideas. Okay, good ideas about your data. Secondly, this naive method can actually be used to if you want to do, for example, like your the MapReduce method, right? You need a starting point. For now, what we do is using the random random start, right? But you actually don't need to do the random start. You can just take in a small segment of data and run a small logistic regression, and then you get a coefficient. That coefficient will be better than your random guess, right? Because that coefficient actually can give you is generated from the data. Okay, it's just not that accurate, but it shouldn't be too far away from it. So in that case, if you start from somewhere closer to your optimum, it actually can converge faster. Okay, so the naive method is actually not that bad. Okay, you can, of course, it's not optimal, but it's not that bad. Now we can see the naive method is not that powerful. Then the question is, can we improve on it? The answer is yes. We're going to introduce next is a method called alternating direction method of multiplier. In short, it's called ADMM. This method is actually a pretty old method. Okay, it's actually the first. I think the first version of it, not first version, is like the first. The origin of this method is actually published more than 60, 70 years ago. Okay, that's even like everybody in this room even was born in that time, even before the computer become more popular. At that time, they have the idea they call the parallelized optimization. Okay, because when computer was not invented, so-called parallelized optimization is just like a theoretical game. Okay, there's no way to implement it. But even with that, that's how amazing the thing is. Even like 50, 60 years ago, when people does not really have a computer, and the theoretical work actually went far away. Okay, went far away. That method was so advanced at that time, nobody even paid attention to it. Okay, until this 2011, there's a professor at Stanford called Professor Steve Boyer. He published a paper which is introduction to the introduction to the ADMM, in the paper is actually review paper. It's not a it's just review paper of all the previous work. And then that making this ADMM method become sort of like popular, be recognized in the field, particularly with the parallel optimization. So which is also can be applied to the big data analysis, which is very, very well. So then the core of it, okay, the core of it. Basically, what do we do is we need to set up a new set of constraints. Okay, so the constraint is what we're gonna do is we're gonna partition our data. Say you have big data, partition our data into like 1,000 small chunks. Okay, small pieces. Then for each small chunk of data, we're still gonna run regular logistic regression like we did for the naive method. Okay, so then you have your big data. Okay, you kind of like D1 up to like DK. So for your you have this is your big data, right? So this is your big data. I'm using the big D here. Big data. Now for each data, you partition them into small chunks, D1 up to DK. For each D1 and DK, you can run a logistic regression. Okay, you can have like a beta one. Beta one. This just means it's from the first chunk of data up to like this is a beta K. Okay. What the ADMM is going to do is you have an extra step. Okay, the extra step is in order to have a global maximization. What I'm going to say, so the constraint, the new constraint, okay, this is a new constraint. So the new constraint is, I assume I have a global beta will be equal to beta K, okay? I'm going to find additional constraint. The constraint is I want to constrain all the beta you estimated from the subset of each subset, they have to be the same. Okay. If you're having this additional constraint to it, so you kind of force it, okay, kind of force it, the beta estimation from each segment, they have to be the same. In this way, we can, if we iteratively go through it, then we can actually ensure the global maximization. Okay. But of course, this is how you do it. That's this is what we're gonna spend probably next like 2 weeks. Okay, we're gonna talk about why it works and how it works. So the advantage for the ADMM is we can guarantee to converge a single machine logistic regression on the entire data set with a reasonable number of iterations, right? So the goal is we don't want to be too slow, right? We still want to achieve this is a global optimization at a reasonable time is reasonable iterations. So that's so this is where we're going. Okay, so we're gonna spend some time for the ADMM. Now to introduce the ADMM, okay, if I directly jump to the ADMM, this is actually may cause I think is for some of you is probably too so like too math involved, too much math for the class, and this is from my previous experience, right? The people actually get stuck with the simple stuff. Okay, is from the knowledge you actually already have. Believe you already have everything to understand ADMM, but it's just some of the knowledge become rusty. So that's why before I introduce ADMM, I actually add another section, which is actually it's a little bit silly in a way. That is this is knowledge from this is a introduction to the optimization. Most of the knowledge actually you should already know. Okay, but some of it you may become like a little bit rusty. I still want to after I like did this is because when I first time teach this class, I didn't have this slide at all, and then I find some students have been difficult to follow the notes. Then later on I put this in. It seems like did is better because this is also serving. So I'm going to introduce do some slides. Okay, so called brief introductory optimization. These are mostly undergraduate calculus. Okay, so you should all the stuff in here you should already know. Okay, if you don't know that's a problem. Okay, but this is going to serving more like as a refreshment. Okay, refresh your mind. If you become some law become rusty, now is time to bring it back. So this actually has three purposes. One is we're going to talk about a gradient, introduce a gradient method in a more detailed way. So now if you went back to the logistic regression, look about this is a gradient algorithm. Yeah, I think it's you should have better understanding. Second all is we're going to introduce this is so-called the optimization condition, which is the KKT condition. Well, this condition actually is useful for me to talk about like SVM later on in the class. Okay, later on class. And third one is if I'm talking about this is the duality problem. Okay, this is like a prime or dual problem. This problem it will become it will be helpful for me to introduce ADMF. Okay, so I think this is although this is slides are very simple, you probably know most of it, but I still want to spend like probably one class or a little bit more than one class to talk about this material. Okay, just to refresh your mind. Okay, so if you know if you most this is the material looks familiar to you, that's a good sign. Okay, that's actually a very good sign. I do not intend to introduce new stuff here, but it's just serving as a memory refreshment. Okay. Now I'm gonna starting with in the three. So this is gonna basically cover the optimization like three topics. One is the maximization without constraint. It's called the unconstrained optimization. Okay. Then then after we talk about unconstrained optimization, then we're gonna go into the constrained optimization. The constraint optimization also has two sections, subsections. One is constraint with equality, right? Then the second is a constraint with is inequality. Okay, so these are the this is where we're going. So the general statement. So we're gonna talk about unconstrained optimization first. So the general state. Oh, another thing I want to do here is apparently in the optimization field, right? People are more talking about minimization problem. Okay, minimization problem. So I'm gonna just using their terminology. Okay, because I borrowed the slides from the optimization field. So I'm gonna just talk about the using their term. So the problem here is a minimization problem. But the minimization problem, maximization problem, they are the same, right? Because minimize a function essentially is maximize a negative function is the same. Then also the concave, convex. This is also just switch, right? For the minimize the function, we talk more like the convex function, right? So for the maximizing, we talk about concave function. So that's again, it's just a different terminology, but the technique and the argument are the same. Okay. So the general statement is give a function f. Okay, f is a map from the Rn to R. This is a function Rn. This is our primary space. Right? We want to maximize or optimize over some n-dimensional space. So your primary space has n dimension, and the f function is a map from n-dimensional space to a real line, right? That just means the f function is you just become one value, and the set S. This S is belong to the n-dimensional space. So we want to find value x star belong to this set such that this fx star is less than fx for all the x in S. Okay. So if you can find a value x star such that fx star, which is valued at f, right? Evaluated by f is less than or equal to all the other x, in your subset in the set X, we call this X star is a minimizer or the minimum of the function F, right? So that's this is just the definition for the minimization of minimum. So this is very it's straightforward. Now we just said it just suffices to consider only minimization. Maximum is of F is the minimum of negative F, right? So that's this is easy to understand. Now the objective function F, okay, is usually differentiable and may be linear or nonlinear. So if it's linear, then and also constraints are linear, then it's become the function like linear programming, right, or the quadratic programming. So that's a set of the domain or the classes for the if you are interested, I think there are class about linear programming and quadratic programming, right? But we are not going to go touch that. We just assume our F function because we in this class the system we're dealing with is not a linear system. Okay, so we're not going to consider that. We just consider this is our object function F is a differentiable. It's nonlinear but differentiable. So constraint set S is defined by the system equations and inequalities, which may be linear or nonlinear as well. So this is set S. This I call the feasible region, right? It's called feasible region. It can be defined by a set of the inequalities. So the any point in our set S are called the feasible points, right? So the set is called the feasible set. S is our feasible set. Any point S into that we call the feasible points. So if S is Rn, if S is just the n dimension space, then the problem is unconstrained. Okay, so we're gonna start with this unconstrained the problem, which is we don't have any constraint on our X. Okay, on our X, so there's no constraint. In here we have this is so-called the global versus local optimization. If global local optimization, we can see just from the graph in above, right? You have two minimum points. You can see the second point here. This is a global minimum, and you also have a local minimum. I kind of already explained a little bit about the why we care, because in most numerical methods, what we find is just the local minimum, right? Depending on where you start. If you're starting from the place closer to the local minimum, you're gonna end up with local minimum. If you're starting the place close to the global minimum, you're gonna end up with global minimum, right? But there's no guarantee. The thing is, from most numerical methods, there's no guarantee you're gonna achieve the global minimum. So local minimum just means your fx star is less than fx. This is only for all the feasible x in some neighborhood of x star, right? This will be a local minimum point. It's just in some neighborhood of the x star is a minimum, but it's not a global, because you see there's another point which is a little bit farther away, but it's less than that one. Okay, so that's so there's a distinction between the global and local optimization. Most of the cases, again, we only can achieve local minimum. Okay, if you want to prove global minimum, this is actually a pretty hard task. So the global minimum, finding or even verify global minimum is very difficult in general. Because if you want to verify, well, most of the cases you have a global minimum, okay? But find a global minimum is very, very difficult unless your function is so-called function is a concave function, right? Concave function, which is something like this, right? Something like this. This is not concave, convex. Okay, if a convex function, then this is you find a global minimum is same as find a local minimum. So that's but most optimizing method, you can design just to find local minimum, okay, which may or may not be global minimum. So if a global minimum is desired, one can try several wide separated starting point and see if they produce the same results. If you try the several like a wide separated starting point, and if you just see the same results, then that gives you some confidence. I mean, there may be just one minimum, okay, which is global minimum. But for some problems, such as linear programming, global optimization is more tractable. Again, a linear system is easier to deal with, but unfortunately, our probably is not in that space. Okay, so we are not talk about that. There are some conditions. Okay, if some conditions, if it's met, then there's the existence of minimum. So the conditions are, so if your function f is continuous, okay, if it's continuous on the closed and the bounded set of S, then your f has a global minimum of S. Okay, so there's a definition is a closed set and also is a bounded set. Okay, the closed and bounded basically is, you know, the set. If you see the if x, let's see one-dimensional space, right? If x is bigger than equal to a, is less equal to b. So this is closed and bounded, right? Closed, that means this is on both sides equal point belong to this is in our set S. So then in this case we see x belong to a and b, right? So that means it's closed and also bounded on both sides. Then if it's x belong to, say, is a to b, if it's open bracket, that means is x is less than b. So that means it's open on b, right? So that's open. Close and open is b. Close and open defined on the boundary, right? Is the boundary point is you have it or not. So the boundary just means do you have a maximum point, right? Do you have you can bound it? So that's this is closed and bounded. So if f is continuous on the closed and bounded set, then f has a global minimum on S. Now, if S is not closed and is unbounded, okay, then f may have no global or local global minimum S. Okay, may not have it, but it may also have it. Okay, and this is just saying if it's not closed and unbounded, then we need additional assumptions. And the continuous function f on the unbounded set of S belong to the, this is coercive. Okay, is coercive if the limit of fx, when the x goes to infinity, the function fx is to the positive infinity. Okay, so then if it's if we have this, then, or in other words, the function fx must be large whenever the absolute value of x is large. Okay, so in this case is then we call the function is coercive. That's just basically saying when the x goes to the infinity or x becomes very large, your function value is also very large. So therefore, the minimum point cannot happen at the infinity. Okay, so that's what it says. So if the minimum point cannot happen in the infinity, the minimum point has to happen in somewhere in the middle, right? In the middle. So then it's just saying if coercive unclosed unbounded set of x, then f has a global minimum on S. Okay, so that's just saying because it's unbounded, but it's closed, right? Although it's unbounded, we know when x has become large, your f is large. So the minimum point cannot be on the end. Then therefore there must be a global minimum somewhere in the middle. Okay, in your set S. So that's what it says about the existence of a minimum. Another concept is about the level set. Level set of function f, that means is a set of all the points in S for which function f has some given constant values. Okay, so then in definition is some like for some given gamma, the level set is going to be, so that's a sub-level set. Okay, so the level set gamma is if we define as for all the x belong to the S such that fx equal to s, okay, equal to gamma. Then this is we call the level set, right? So if then this you can imagine is like this is a contour, right? This is like a contour of the function. So for the sub-level test is for all the point x belong to S, fx is less than equal to gamma. Then this is the L gamma we call the sub-level. Okay, sub-level basically that's define all the points which is smaller than the gamma. So if your continuous function f has a non-empty sub-level, set that is closed and unbounded, then F has a global minimum on S. What does this mean? So if you can find, okay, if you find this is a function F has a non-empty, if you sub-level, if you choose some the value gamma, okay, this is value, which means if Fx less equal to gamma, this set is non-empty, then there must be a global point. Okay, there must be a global minimum point. This is just by definition. There will be a point X which is going to reach the minimum, right? So if S is unbounded, then F is coercive on S if and only if it's all of its sublevel sets are bounded. Okay. If you don't follow this statement, that's just understand whatever, like how much level you can understand, because really these are concepts we can set it up, but not really, we're not going to really use in our argument. Okay, but yeah, I think it's just for the rigorous of the optimization. I think it's better to it's good to include this concept, but it's if you are confused at this point, you can just let it go. Okay, it's not that important for the that's more like for the theory. Okay, it's not important for the algorithm side. For the uniqueness of the minimum, we need to introduce a concept called convexity. So convex concept, this can be defined as uniqueness of the minimum. We have two sets of the convex concepts. One is on the set S. Okay, so if the set S is convex, that means if it contains a line segment between any points of these 2 points, so if you pick up any 2 points from a set S, you contain a line, you draw a line between these 2 points. And this is all the whole line is still in the set S, then we see that set S is convex, okay? So it's a convex set. Now, convex set is we can actually see it from let me introduce the function X, then I can draw on the whiteboard to illustrate the concept. Okay, so the function F, you can also see the function F is convex. Okay, so if function F is convex on some convex set S, if its graph along any line segment in S lies on or below the chord connecting function values and endpoint of segment, then we call the function F is convex. Now, definition is if you're just reading from definition, is kind of like is a little bit confusing, right? But if I draw some graph to it, then you will be able to see. So if you have a set S, right? If you have set S, if you pick any 2 lines from this S, and if you draw a line between, if you pick any 2 points, okay, and you draw a line between them, the line still within this set S, then the set S is convex. Like this example, this set is convex, right? It's a convex set. And you pick these two, okay, any 2 points, okay, you draw a line between it, it's convex. This set is not convex, okay? This set is not convex. Because if you pick 2 lines, if you pick a point here and you pick a point here, you draw a line, you see some of it is not contained the set S, right? Some is outside X. So this set is non-convex, okay? Is non-convex. You can just draw any, you can use this example to check in like in general, okay, unless it's low dimension, like for our cases, it's very hard to verify the convexity of the set, okay? Because our physical point could be the geometry of the constraint could be very complicated, okay? But this is if you can show it is a convex set, then you're actually in a pretty good shape, okay? That's why the linear programming and the quadratic programming is so well studied, because they can define this convexity in a pretty good with pretty good confidence. But if it's long linear constraint and high dimension, sometimes it's very hard to prove this convexity. So this is convex, okay? So convex set is pick 2 points, draw a line between them. If the line is still within the set, it's convex set. Otherwise, it's non-convex. For the convex function, okay, But the convex function is basically what it is saying like this. If you draw a function, you pick two lines between them. Okay, pick 2 points on the line, and if you draw a line between them. So any value between these two values, the function value is at or below this chord. Okay. So if this is how we call this function is a convex function. Okay. So convex function is basically you can think about like a bowl. Okay, a bowl. If you can your shape of function, if you can the bowl, if you can hold water, is convex. Right? If you cannot hold water, then if you go like this, this is convex. Okay, below here this is concave. Okay, this is another. If it cannot hold water, is going other way is concave. So this is convex. Is doing like function. Some function can be neither concave or convex, right? Because say if you have a function, if your function is going like this and also like oscillate function, right? Like a sine or cosine function, then part of it is convex, part of it is concave, concave. Then there's no convexity. Okay, so convex function it has to be for any 2 points on line. You draw a coordinate has below the value of the f has to below or at the chord. All right, so that's the convexity. So this is a two graph basically explain this is a convex set and a convex function, which is a little bit hard to just say it from from word, but from graph is very simple. Now convex optimization is kind of like it's kind of like a wishful thinking for the in the real life. Okay, so if you think about the optimization problem, okay, if we draw the whole optimization problem, if we're using the circle, okay, to define all the optimization problem in real world, okay, we want to solve, okay, so that circle is the whole. This is like optimization universe, right? It's all the problem in our life to try to deal with in reality. Convex optimization is this tiny spot right here. Okay, so which means convex optimization is only account for very small fraction of problem. Okay, very small problem. But if it's outside of the convex problem, then this is may become extremely important, hard to evaluate. That's become like this is become almost intractable. Okay, now most of literature, almost like more than 90% of the literature, okay, or even more literature, we are talking about convex optimization. Okay, this is accounting for like a bigger 90% of the study is on this tiny spot. Okay, and then all the rest is only account for the part all the rest study on this is uncharted region is a very small fraction study. This is because if your problem is in a convex sense, okay, you actually in a very good shape. You can solve it pretty easily. If it's not, I would say you're in trouble. Okay, that's in a simple you're in trouble. But you can most of the time people just pretend. Okay, pretend my problem, although it's non-convex, I pretend it's a convex problem. Okay, I just solve it in a way. Again, that means you're probably going to find some point. Okay, going to somewhere may not be the global optimum, but it can still have some value. Okay, so that's again it belong to the like something is about like a something is better than nothing. Okay, so that's kind of how we do it. So if it's non-convex, we kind of we need to be careful. Many of our problems are indeed is a convex problem. Okay, we can actually show like logistic regression. Many studies we can show that it's a convex problem. But there are problem could be non-convex, like the neural nets, okay, then they may not be a convex problem, okay. Any local minimum of convex function f on the convex set S is a global minimum of x, right? So if your function is convex, that means you only have one minimum point, okay? So if you can find a local minimum, it's guaranteed to be a global minimum. Any local minimum of the strictly convex function f on convex function x is unique global minimum f, okay, on S. So that's just the convexity. The first order optimal condition is for function with one variable. One can find an extreme by differentiating function and setting derivative to 0. So the generalization to the function of n variable is called the critical points, right? So the solution of the nonlinear system, if you're taking the gradient of a function f with respect to the f, if set it equal to 0, and solve it, then this x is we call a critical point, right? So what you have in this is the inverse of the delta, right? This is a function of the triangle. Inverse the triangle. This is a sign of gradient, right? So that's a gradient. This is a gradient function of f, whose s component essentially is just the partial derivative of fx with respect to the xi, right? This is our if you're setting your gradient equal to 0 and you solve the equation, you get the critical function. So for continuous differential function f, any interior point x star of S at which f has a local minimum must be critical point. Okay, so that means if you have a minimum point, that minimum point must be a critical point, or in other words, it must satisfy this equation. Okay, nonlinear equation. But not all the critical points are minimal. They can also be maximum or the center point, right? So if you have this is a if you have a function looks something like this, okay? If you're using the setting the first order derivative or the gradient equal to 0, you can find out the function like this in here. These are all critical points. Okay, critical point just saying your first order derivative equal to 0, but it doesn't say it's a minimum. Okay, so and also critical point could be setter point, right? Setter point that basically means it will be some points where your gradient can be go up and then go down. This would be setter point, right? This would be setter point. So you can there are places where your gradient could be 0, but it's not the minimum or maximum. Now, to ensure it's minimum or maximum, that's where the second order optimal condition come into play, right? So if you do the twice continuous differentiable function f, if we can calculate so-called Hessian matrix, okay, Hessian matrix H is basically a second order derivative of the function f with respect to the xi and xj, right? We already talked about concept in the Newton-Raphson the Newton-Raphson method. So then the critical point f x star, if this Hessian matrix is positive definite, then the x star satisfies the first order condition is a minimum, right? If it's a negative definite, then the x star is maximum. If it's indefinite, then x star is setter point. If it's singular, okay, then the various pathologic condition is possible. In that case, we need to you don't have a good optimization problem, okay? So we need to sort of like check in like a case by case. So what we have in this condition, so this is a condition we can be applied to the Newton-Raphson. These are the sort of like the basics, okay, set up for the problem. So then next, let's go through the again. For many of them, these are just terminology. Okay, I expect that hopefully this can refresh your memory a little bit. So then the next, what we're gonna do is we're gonna go through this is unoptimized the condition. So we're gonna talk about a golden search using like a simple case. Then what we're gonna do is we're gonna talk about the constraint and unconstrained or constraint optimization using equality constraint or the inequality constraint. Okay, so let's leave in that to the next class. as I have a few minutes left, I want to take in the time to have two reminding items on the Blackboard. One is I get an email asking for the group projects, okay, and also getting the email for the ask about final exam. So I want to spend a few minutes talk about the projects. Right now it's already almost end of October. Okay, so the class is actually went a little bit slower than I expected. So what I'm gonna do is so there will be only originally I said there will be four projects, right? As take like individual projects plus one final project with a group project, right? So for now, given the time, what I'm going to do is you will only have 3 individual projects to work on, okay? So for the 4th project, I will give you guys as a gift. So everybody will get 100 on your 4th project, okay? You don't need to do that because you will not have time. So you still have 4 individual projects, but the 4th one, you're going to get a 100 on that. So we will have in one individual project, which is using logistic regression, use ADMM to implement logistic regression. Okay, so that's will be, I can tell you, that's will be your 3rd project, which is going to happen in early November. Okay, which is going to assign early November. Now, for the group project, what are you going to do? What I'm going to do is like this. Well, I'm going to randomly. So assignment group, your teammates will be random assignment. You know, you cannot pick your own the teammates. I will do use a random generator. Okay, so you will be have your. So just wait until assignment. I will provide some topic like the candidate topic for you guys to choose from, or you can choose your own depending on you can discuss with your classmates. So the final group projects, what you're gonna do is you're gonna writing a report with it's do a group project, and then at the end you're gonna choose one person, okay, to present on giving a final presentation in the last 2 classes, okay. So used to be I ask like everybody has to speak up, but we probably gonna end up with have like 9 or 10 groups. So each group is gonna have about like a 7 to 8 minutes presentation. So which is I think is gonna be too hard for everybody to talk. So in that case, each group you're gonna choose one person to present, and then in person. If you're on the in-person session, you will present in person. If it's online, you're on a Zoom, you're gonna present on Zoom, okay? Because we simply cannot hold enough people in the classroom. So this is about the group project. For the final exam, the date has been determined. The date is December 9th, okay? So December 9th or December 8th. It's so the date has been determined. I believe is December December 10th, right? So December 10th. So it's a Wednesday, and I think last class I think December 8th. Okay, so depends on I may not have the class in December 8th because I want to give you guys a little bit more time to study on it, because then if December 8th is the last class, then you only have like 1 day in between for the reading day. So December 8th we may so in other words, our final presentation may be on December 1st and December 3rd. Okay, December 8th I may skip it just to give you guys enough time for the final review. So that's there will be no practice exam because this is a graduate courses. So you just the materials will be the things we cover in the class. It should be everything we talk about in the class, like slides, anything I write on the Blackboard. So those if you attend the class like regularly, and if you went through notes without problem, without like I wrote on Blackboard no problem, you should not have problem in the final exam. Okay. So final exam, there's no coding. There will be just testing some like concepts, okay? Like concept you learn in the class. the algorithm we learned in this class may be applied to a problem, just like Newton-Raphson. You may apply to a new problem, right? So apply this is write a Newton-Raphson to optimization problem. So you may have some this is so you can consider that's as more like you practical side, coding side you already done through your projects. Okay, so the final exam is more passed on the concepts. Okay, on the materials. So that's about the exam. Now for those on Zoom, okay, if you are remote, I will send up to the. So if you're in person, your exam will be in person. For those who are registered on Zoom, so because the reason open another Zoom is we don't have enough seats in the classroom to host everybody. Okay, but I would envision most people who are registered online are still like most students can take the in-person exam, right? So so I will give a push just to the person who are on Zoom or you register online. I will ask you to see if you have problem taking in-person exam. Okay, so let me know because I intend to keeping tell everybody gonna be in-person exam no matter you register on in-person class or the online class. Okay, so I plan to just host like one big in-person exam for both sessions. So, but if you have problem like a issue taking the in-person exam, let me know. So we can discuss about it. Those only apply to the online registration. Okay, so if for those who are registered in person, you have to take an exam in person. Okay, so that's about I want to see about group project and the final exam. Any questions about that?
Yeah. Final exam, if we did the math heavy derivation, would there be any questions like that?
It could be. Yeah. All right, if no problem, then no question, then that's it. I'll see you guys on Wednesday.